So first, I'm just going to go using the exact same structure as before, which is what can we calculate? What are the metrics that we can actually estimate? So first and foremost, we can estimate confusion matrix and a kind of actual confusion matrix for binary classification only. And for multi-class, we can get any of the matrix that are used, and for binary as well, that are used based on confusion matrix. So precision, recall, accuracy, no, I can't pronounce it. That one, F1, and NAF measure. And we can also calculate and estimate ROC AUC, which is also widely used way to evaluate the quality of our models. And we have familiar visualization here. What does it do? Exact same thing, so I won't go in depth here. Captures full impact of coverage shift of performance, assumes there is no concept drift, and assumes there is no coverage shift to previously unseen regions. We operate with the exact same set of assumptions, and we're going to actually leverage similar kind of ideas, but in slightly different manner. So here you see the first difference when it comes to inputs. We actually not only need our predictions, but we also need the model scores. So quick recap, model scores are the numbers between, for just to use binary classification as an example, they are the numbers between 0 and 1 that are supposed to represent the probability that a given data point belongs to a certain class. So let's say if you have 0, you have binary classification and you have output 0.3, it means that there's 30% that a given data point belongs to a positive class. So we also need those, and likely most of the classification algorithms that we use nowadays, especially on any kind of data, provide those scores. We also need model predictions, and we again need ground truth / target, and again, it's only for fitting. And interestingly, we don't actually need our model columns here, so our features, because we implicitly get them via model scores. And again, it outputs the exact same thing: thresholds, confidence bands, and the point prediction, the estimated metric. Now, let's build up the intuition, and the intuition is very similar, but slightly different. So we see familiar visualization here. When we see on the left test data, on the right production data, we see a region that is where the model is very confident, and the region where the model is not so confident. And we're going to see covariance shift towards regions that are not confident. And let's say that the region that's not confident is just a region between two classes. It's close to the class boundary. So of course, the model struggles to correctly predict to which class a given data point belongs, just because of inherent noise in the data. But the difference here is that instead of estimating this contour plot using by training another model using the input features and the model predictions, we're going to directly leverage the model scores, because the model scores already give you this contour plot of model confidence. So that's what we're going to do. That's our intuition. So we're going to, again, leverage that directly. And let me explain how we do it, because there is quite significant difference here. So first of all, as I mentioned, these model scores are supposed to represent probabilities, but unfortunately for most of the algorithms, they actually don't. So what we need to do is we need to calibrate those probabilities. So if you get, let's say, value 0.4, it actually does mean that on average, 40% of data points with value 0.4 will end up being positive. That's just literally the definition of frequentist probability. And we need to make sure that these model scores abide by the definition. Then we're going to choose our threshold, because to make predictions, you need to threshold your scores. So we're going to choose a threshold. Then we're going to do a kind of weird thing, because for most of the metrics for classification, it doesn't really make sense to define them on point-to-point basis, because it's just going to be either 0 or 1, 0 or 1. Let's say you want to have per point accuracy or per point precision. Either the prediction is either right or wrong, and it doesn't really make sense to look at it from per point level. So instead of finding the confusion matrix for every point, we're going to find the expected confusion matrix where the value doesn't need to be 1 or 0, but can be a floating point value. And then we're going to aggregate to find the actual full confusion matrix for our chunk of data. And then from this confusion matrix, we can compute any metric we want, including ROC AUC if we add some stuff here and there. So I'm going to now walk you through every step, starting with probability calibration. So here what you see is so-called calibration plot. I took it directly from scikit-learn. There is no new science here. This is all rather simple. So what you see is we bucketed or we binned our predictions in certain buckets, or let's say every 10% or every 20% in our predicted probability. So let's say we have a bucket here between 0.2 and 0.3. And in this bucket, the average value of the predicted probability is 0.3. And what we want to achieve and what we expect from actual probability is that if we look at ground truth at realized classification results or at targets, we would expect to see, let's say, the 0.2 positives, but we don't. We would expect to see a very straight line here. But we see kind of the sigmoid shape for support vector classifier. And that just means that this algorithm is not properly calibrated. So what we need to do is we need to use very simple regression using this exact plot and this exact bins, and we'll try to straighten that plot to make sure that it forms straight line from 0 to 1. And if we see that the mean predicted probability for a bucket is 0.2, we actually do observe 20% positives predicted on our test set. So that's what calibration is about. So that's the first step. We do that. Nanimal handles that internally, so no need to worry about it beforehand. Then we pick a threshold based on our business, based on our metrics, which is we pick a threshold that maximizes the metric. Let's say the metric is F1. You're going to pick such a threshold that maximizes your F1 by just iterating, or you just pick 0.5 because why not? Then we already know that our predicted probability corresponds in long term over a large number of samples to realized fraction of positives. So we know that if it says it's 0.9, there's actually 90% chance that a given data point is going to end up being belong to positive class. Then we're going to threshold it, and we will know for a fact that a given data point belongs to positive class. So from that, we can actually say that, again, we know that for a fact, there is 90% chance that this is a true positive and 10% chance it's a false positive. And based on that, we can find the expected confusion matrix for every point. And again, we know that we can assign the expectation of 0.9 to true positive and the expectation of 0.1 to false positive, because on average, in long term, that is exactly what's going to happen as long as our predictions are well calibrated. And we also know for a fact that it cannot be a true negative or a false negative because it's above our threshold. So the algorithm itself will always make a positive class prediction. Then we do it for all of our data points in a given chunk. Again, we want something like 700 or more data points. And we just sum it. And what we get here are these, this is kind of this weird confusion matrix with floating point numbers. But again, working with expectations. So we can directly take that expectation and convert it to a metric, such as precision, recall, F1, etc.